Linear loads are characterized by their ability to draw a constant current or power across a range of input voltages. This means that the load presents a constant impedance or resistance, and its current or power consumption maintains a proportional relationship with the applied voltage. Linear loads are commonly employed with low-voltage power supplies, such as those operating at 12 volts direct current, 24 volts alternating current, and 36 volts alternating current. When dealing with linear loads, the neutral conductor plays a crucial role in completing the electrical circuit. In situations where the neutral conductor serves as a current-carrying conductor, which is often abbreviated as CCC for linear loads, the current flowing through the neutral is essentially equivalent to the sum of the currents in the phase conductors. This phenomenon occurs because the electric current must always flow in a closed loop, and the neutral conductor acts as the return pathway for the current to complete the circuit. Article 310.15b fork of the National Electrical Code, also known as the NEC, provides specific guidelines for sizing the neutral conductor in electrical systems. According to this article, for linear loads that are isolated from sources supplying other nonlinear loads, the neutral conductor can be sized to carry the full and balanced load current. The rationale behind this provision is that linear loads do not generate harmonics, which are distortions in the electrical waveform that can lead to imbalances in the neutral current. In practical applications, it is generally considered feasible to employ the demand factor calculation method outlined in Article 310.15b fork for sizing the neutral conductors serving linear loads. This method offers a more precise approach to determining the appropriate size of the neutral conductor, as it takes into account the potential reduction in neutral current resulting from the presence of linear loads. In summary, linear loads are distinguished by their ability to maintain a constant current or power draw irrespective of variations in input voltage. They are frequently used with low-voltage power supplies and exhibit a neutral current that mirrors the sum of the phase currents. Furthermore, Article 310.15b fork of the National Electrical Code permits the utilization of demand factors to calculate the neutral conductor size for linear loads, thereby accommodating the reduced neutral current attributable to the characteristics of these loads. When considering the application of demand factors for existing electrical installations, it's crucial to proceed with caution and thorough analysis. Simply applying demand factors without a comprehensive understanding of the actual load profiles and the potential for future changes can lead to undersized conductors and potentially hazardous situations. Here's a detailed breakdown of the factors to consider when evaluating the practicality of applying Article 310.15b fork due to existing demand factors. Firstly, you must conduct a load analysis. A thorough load analysis is paramount. This involves measuring and recording the actual current draw of the existing loads over a significant period. Data loggers can be invaluable for capturing load variations throughout the day and week. Secondly, identify load types. Clearly differentiate between linear and nonlinear loads. This is critical because Article 310.15b fork specifically addresses linear loads. Nonlinear loads, such as those found in electronic devices with switching power supplies, generate harmonics that can significantly increase the neutral current. Thirdly, determine the harmonic content. If nonlinear loads are present, measure the harmonic content of the current. A harmonic analyzer can provide detailed information about the magnitude and frequency of each harmonic component. High harmonic distortion necessitates a more conservative approach to neutral conductor sizing. Fourthly, check the neutral current. Directly measure the current flowing in the neutral conductor under various operating conditions. This will provide a baseline for comparison against calculated values based on demand factors. Fifthly, apply demand factors cautiously. Even if the initial load analysis appears favorable, apply demand factors with caution. Consider the potential for future load growth or changes in load types. If there's a possibility of adding more nonlinear loads, the demand factor approach may not be appropriate. Sixthly, ensure compliance with other NEC requirements. While Article 310.15b fork allows for reduced neutral conductor sizing under specific conditions, it's essential to ensure compliance with all other applicable requirements of the National Electrical Code. This includes ampacity ratings, overcurrent protection, and conductor dirting factors. Seventhly, consider worst-case scenarios. Evaluate worst-case scenarios, such as simultaneous operation of all connected loads. Ensure that the neutral conductor can safely carry the maximum possible current without exceeding its ampacity rating. Eighthly, document your assumptions and calculations. Thoroughly document all assumptions and calculations used in determining the appropriate neutral conductor size. This documentation will be invaluable for future reference and for demonstrating compliance with code requirements. Ninthly, consult with a qualified electrical engineer. When in doubt, consult with a qualified electrical engineer who has experience with load analysis, harmonic mitigation, and the application of the National Electrical Code. An engineer can provide expert guidance and ensure that the electrical system is designed and installed safely and in compliance with all applicable regulations. And tenthly, remember safety first. Safety should always be the top priority. If there is any uncertainty about the adequacy of the neutral conductor size, it's best to err on the side of caution and install a larger conductor. Undersized conductors can overheat, leading to insulation damage, fire hazards, and potential equipment failure. When evaluating the practicality of applying Article 310.15b due to existing demand factors, it's imperative to conduct a comprehensive load analysis, carefully consider the types of loads connected to the system, and account for the potential for future changes. Blindly applying demand factors without a thorough understanding of the electrical system can have serious consequences. Always prioritize safety and consult with a qualified electrical engineer when necessary.